All right, thank you for the introductions. Again, my name is David Liu. I'm the Python Technical Consultant Engineer for Intel, and with me is Anton Malakov, who works on a lot of the topics that we'll be talking about today. So to kind of give an overview of the area that I want to speak about, there's a lot of packages and developments that have gone into the concurrency and parallelism fronts in Python. Then we'll talk a little bit about kind of what nested parallelism and oversubscription is, and then a few methods of composable thread control that can be applied to them, how some of these packages and efforts can work under the hood, a little bit about what Pythonic style actually means for these packages as well, and what the future of the Pythonic style for this type of parallelism is. So to kind of give an overview of what the current state of the Python concurrency and parallelism is, we've had a large amount of packages over the ages that have been developed, and this is just a short list of them, of the kind of the big key ones that have developed since then. And you can see from all the way from 2008 up until now, there's just been kind of consistent level of frameworks that meet in different areas that have been applied to concurrency and parallelism. So with a few, we have, I believe we actually have a few of the developers for some of these packages here at this conference as well, so this is kind of an exciting time. So again, we actually have the options in this space for parallelism and concurrency are very good compared to other ecosystems. And majority of these play well with the global interpreter lock or the GIL, and walk around it with distributed or vectorization techniques. And in the more domain-specific areas, typically you can rely on high-end C implementations that actually harness parallelism at the C level. Like SciPy and NumPy do a great job of this. And the recent trends have shown that there's an increasing core count being applied towards the things that we're running Python with. So nested parallelism and oversubscription are now quite possible in these kernels, and I'll go into that in a little bit. But first, I'd like to talk about kind of the GIL and why we use it and what it's good for. So I'm sure as many of you have been in this space, many complaints have been filed against the GIL in the Python space, and many efforts have been tried to remove the GIL. Sorry if any of you came to hear like a GIL removal talk, this is not one of them. As it stands, there's a lot of main tenets of what the GIL guarantees that we really, really like, right? So predictable behavior, read-write safety for Python object access, and ensuring like the reference counting doesn't get kind of borked or anything. And it also makes extension module development easier for those of us who are writing the extensions. So, the guarantees that the GIL provides really make it a strong suit for, keeping it in. So, for that reason, the GIL is really a non-issue when it comes to the development and the use of these frameworks. But the reason that I say that is because there are many ways of stepping around the GIL itself. So again, SciPy and NumPy are great examples of this, where the command is sent to SciPy and it gets dispatched to the BLOS implementation, such as the MKL or OpenBLOS, where things are then vectorized and parallelism is applied at that level. And there's a lot of frameworks in that space that operate to try to directly access vectorization and bring that to an even lower level in a Pythonic manner. So Numba, NumExpression, Cython, they all do this. So for that type of control, we do have an extraordinarily great set of frameworks in that space that a lot of other languages don't have. Multiprocessing frameworks are also, a big advantageous area that Python has provided us. So, you can separate things into separate processes. So the types of abstractions that are provided are pretty good for this space as well. So exiting the GIL is, generally the best way of being Pythonic-ish, right? So like if you say, okay, instead of removing the GIL, we're just going to step around it, we're going to drop into a mainline like NumPy or SciPy and then get around it, is kind of the most Pythonic way possible. The composition of abstracted flows is where I think things can get a little more complicated, especially if you split off into multiple processes and multiple threads based on those processes. And again, it's quite rare to absolutely necessitate a language to be completely thread safe, and that's where a lot of the advantages of Python's type inference and everything else would go away if we did that. So, with that being said, let's talk a little bit about the spaces that are covered in this area, right? So if we were to split into 3 different areas, we have application level parallelism, data parallelism, and then single-threaded concurrency. And you can see where a lot of these packages end up sitting in these kind of this Venn diagram of what the spaces will cover. And as you can see over here on the right side, with NumPy, SciPy, Numba, and Cython, num expression as well, you have a large set of data parallelism focus items that are high vectorization. On the other side, you have multiprocessing. On the bottom left, you have a lot of the asynchronous frameworks that are commonly used, or concurrency-based frameworks that are commonly used in not just numerical space. So if we were to remove that bottom one and just focus on these 2 right here and expand it again, we'd end up with this, which is one that's Python multiprocessing, one that's Python multithreading, and then one that's just focused on data parallelism. And if Matthew Rockland's in the house here, he'd probably be really happy that Dask is sitting in the middle of all of that. But now taking a look at, going back to the original topic, why am I even coming up here to give this talk today about multiprocessing and multi-threading, is that there's a problem that now can exist if you kind of travel in between these areas, which is that nested parallelism and oversubscription can occur because of the way that we are composing these levels of parallelism. Right? So, let's take this area of focus here. So this area where it's between multiprocessing and between data parallelism and between multi-threading and kind of all the areas where it falls in between, and expand that. So to kind of give you a good idea of what this parallelism will look like, here's a great example. You have your pool, which is a multiprocessing pool, that then extends to a thread pool, and that you then do a pool.map. But within that pool.map, you're then calling NumPy. Well, then what does that actually do? You then have p threads, p number of threads, and then you have the ones that are then called by NumPy, and then you start getting a lot of threads that you really didn't think were going to occur, or you didn't intend for this reaction to occur. And what that gives is a whole slew of things that then end up in oversubscription. Oops, there we go. So some fun diagram here. You go from threads, and then you go to a kind of a tangled mess of threads, because now it's trying to spawn off many threads where it shouldn't be, because you don't really have control in that format of composability. So the overheads that then occur from that, right? You have the direct OS overhead for switching out a thread. The CPU cache becomes cold. Lots of not so great things, right? And a lot of these machine learning frameworks actually implement this multi-tiered type of composable parallelism, and they run into these problems. And we do work with a lot of them to try to identify these problems and try to find ways of solving it. Right now, kind of before our efforts in this space, the most of them would just set OMP num threads to 1, or KMP block time to 1 or something. And SMP ironically addresses this, which I'll go into later. So again, let's talk about now the composability models that we've been working on at Intel to kind of address this space, which is that TBB4Py, which is a free package, comes with the Intel distribution for Python, is a C extension package manager for managing nested parallelism, and it does it through the dynamic task scheduling of the threading building blocks that Intel has. And it instantiates via monkey patching. So you actually call that the TBB4Py package, and then you call your normal script, and then it actually monkey patches in the thread pool to be able to have that dynamic task with the threading and everything. And then it dynamically maps tasks onto coordinated pools to avoid the excessive threads. The other package that does this is static multiprocessing, and this was kind of premiered last year. It's a pure Python package that manages nested parallelism through coarse-grained static settings. So what it does is it takes the settings that were meant from each of the multiprocess level areas, and then continues to pass those settings down to the threads that get, the processes that eventually will take those and create more threads. And it uses a bit of affinity, mask, and OpenMP settings to statically allocate the resources to avoid excessive threads. So now coming back to the nested parallelism again, now if we take this trouble spot and we look at what these two areas are trying to solve it with, TBB's thread coordination system is doing it by limiting itself to a pool. So all of the threading will go through the given pool. And then, if one ends up finishing a little early, it can actually be transferred back and it can take one. So for things that are dynamically tasked where you have, threads finishing way earlier than other threads, this is a really good use because it can handle these type of constraints. SMP's total threading affinity system does it through a slightly different way. So again, remember what I was saying about passing those settings down. It's taking what you have for your application, and then if your thread pool, you want to apply those settings all the way down, SMP will actually take those and apply your settings and augment your MKLR BLOS threading at that point while maintaining your settings. So it accomplishes the ability to fight oversubscription in a very different way. And that is running under the SMP module. So now I'm going to bring Anton up, and he's going to show us a demo of what that looks like. And so here you go.
Hello, glad to be here. And here again, and basically I'm glad that I can finally show some live demo here, if it works. So first of all, let me show that the demo will be, it is already published on the GitHub. And for more technical details, please refer to the paper of the published in the proceedings of this year. So what we have here, we have several packages installed. So first of all, MKL is needed for this composability mode with TBB. Thus, we have NumPy built with MKL. And we have this SMP package and TBB for Py packages. And let's right away start this one. And I will explain what it does. So I can see on this corner of the screen that it's basically a very simple program similar to what we have on slides. We have some thread pool, we prepare some data, and we just map, basically running in parallel, linalg QR decomposition 3 times. And as David explained, we have nested parallelism here because we have this pool of threads, thread pool Pythons, and we have MKL parallelism here. So it works kind of very slow, so let me interrupt it here probably. So we have 40 seconds to run. So now let's start some SMP. Yeah, fast. And TBB. Also fast. So that's pretty much it. The modules have kind of help command line, and they have some fun options to to set KMP block time. SMP also introduced recently kind of helper to enable OpenMP composability, which I described last year. Well, thank you, David.
All right, thanks, Anton. Now I have to go all the way back. Okay. So kind of in review, so with what you saw in the demo there is the ability to handle with a very large amount of cores on your system. What you saw was taking 40 seconds was the fact that it was getting oversubscribed in the fact that it was passing one level of parallelism to the next one, and it wasn't being able to communicate or pass down the settings. And both of the two that were shown, TBB for Pi and SMP, are able to handle that type of large amount of core work by then providing a mechanism for control or either that or passing down the settings. So, and they do so by different methods. So again, now much of the concurrency and async areas, going back to original topic here, are rich with packages that solve in those areas. And the true parallelism is a small but strong area. So focus is generally been towards like concurrency and asynchronous offerings. So most of the ways of achieving parallelism are generally through vectorization frameworks and multiprocessing or distributed, and you've seen that through a lot of the packages that I listed at the very beginning. There's been kind of a big push for those packages. So I think one of the main questions that I want to bring up in this talk is like, how do we do so in a semi-Pythonic way, right? Because at some point you're either going to be negotiating C, you're going to be negotiating something that is not the most Pythonic to implement and adds build complexity. So that's why I wanted to bring up that topic. So I kind of came up with this question of Pythonic-ish, right? Does it have relatively few code changes? Does it modify current behavior? Do you have to modify your current behavior of a framework to fit your need? Is it directly in the Python standard library? Is it writable from the Python layer? Is it an easy interface to understand? Like, do I need to read a huge manual for this? And do you keep yourself in the Python layer as in terms of what you're writing, right? So if you say, oh, this is, this package does parallelism, but then now I need to drop into like, a completely different language to do this, or I need to drop into an intermediate representation, that's kind of painful as well. So the question is how close we can get, right? So if we take this rule and these rules and then look at it under the lens, we can then analyze, say, TBB for Pi. So for TBB for Pi, it has, it meets, I think, like 4 out of the 6. It's not in the standard library. It's not directly writable from the Python layer. So that's kind of, it shows one way of attacking it, but not exactly the most obvious. The interface is relatively easy to understand because you're just calling it, and then you can have a command line argument that just then defines the size of your pool. Also keeps you in the Python layer. When we look at SMP, it's a little better because it is semi-writable through the Python layer. Again, both of them are not in the Python standard library, so it still is like a different download. There still are things that you do have to learn about it when you utilize it. Most of it is about which rules it passes down. So that's when we look at the lens of Pythonic-ish, it does an okay job. And then I think that then brings up the question of like, what is the Pythonic-ish style for parallelism, right? So like, how realistic is it to have a firm requirement on for a pure Python implementation? Like SMP is pure Python, TBB is not. Like, is it a high requirement, is it a low requirement? I think that's like a community, kind of a community thought process that we might have to go through. And also, what is the best way to modify Python code? I think that question came up a lot. Like, we both of the TBB for Pi and SMP both do monkey patching. So at that point, is monkey patching the right way of doing things? Should we be looking at a different type of framework? At what level should the parallelism be controlled? Like, should it be at call time? Should it be at the code level? Like, where should it be? It should be programmatic. And can an interface be agreed upon to operate on parallelism? I think this is where Concurrent Futures did a really good job of stating, this is the way that we like to have it said. These are the calls, this is the behavior. If you can fit this and you're compliant with it, then your framework can be kind of used in that space. Do we have anything that we've come to consensus to on this? So, looking at these questions again, in the lens of what we have, and I guess a bit of the work that I've been doing, how realistic is it to have a firm requirement for pure Python? Probably not required, but highly recommended. How about modifying, how much to modify the Python code through monkey patching? Seems to be the new normal, right? From all intents and purposes, a lot of people have said monkey patching is okay. A lot of the framework developers have said, so I guess we're going to run with that. At what level should parallelism be controlled? I think that question always comes up because at the Python layer, it seems to be a good idea. Some people say it should be a lower level. Some people say it should be like, in your environment. I don't know. Maybe you should have directives for how additional layers can be composed for best case. Like that is one way that other languages have accomplished it. And can an interface be agreed upon to operate on this parallelism, right? So, I think the jury's still out on that one. In every iteration of these attempts, like, both of these are attempts at trying to solve and trying to propose, where should the direction of concurrency and parallelism be going, especially at this parallelism level that deals with oversubscription, right? And hopefully through these efforts, we have a more clear picture. So, in summary, TBB4Py and SMP attempt to address, the Pythonic-ish mentality and methods by augmenting the way that we use multithreading and multiprocessing. So we try not to change the underlying code. I guess it's best to have these two forms of multiprocessing and multithreading at the same level, so Python level and C level, and leave them, kind of semi-separated, and then leave the domain-specific stuff to the frameworks. And perhaps another weird thought is like, well, if you're leaving threading and multiprocessing directives, doesn't it just sound like, saying pragma OpenMP or something, leaving directives? So it's like that. I think these type of questions are really interesting to think about as we progress farther in this space. And then having more augmentable threading behavior is pretty useful, and but that also means that putting a lot of the bulk of the responsibility on the framework developers and the users that's where a lot of that responsibility will then fall to. And is that correct? That's still a thought to be put out there. And then threading for numerical there's a lot of frameworks in this space, and I think for non-numerical, it might be possible, but there would probably be some concessions to, the data type may not be as open as just standard Python object. So the ecosystem is at a critical mass of good frameworks. So I'm really excited to see what comes from it. So hopefully, from the two packages we've shown today and some more work in the industry, let's see what we can come up with. All right. Anton, if you want to come up for the questions. Yeah.
So we have time for some questions. There's a mic there, and I can also come over to anyone nearby. I can't quite see too well because the lights are on me, so if you could just raise your hand, I can come by.
Question. Thank you for the nice talk. And this goal to have the shared parallelism across the whole Python process is good, and across processes is great. Technical issue and a kind of question about TBB, you can only build it statically, or shared, it has to be shared, which makes sense as a shared library. And then this works in Conda, but for wheels, Python packages, and sharing a TBB, the parallelism, the scheduling across the whole process. Is there a way to approach that, or ever a way to tackle that problem?
So am I understanding it correctly that statically, do you mean the scheduling statically or linkage of TBB is static? What do you?
Yeah, so they're related, right? It needs to be, all the Python modules need to be using the same shared library, and so then the scheduling can be shared across the process. But right now, wheels don't support shared libraries as well.
Well, I mean, the TBB is dynamic library, and actually they don't want to be as a static library because otherwise, like, the promise of singleton is lost, and actually TBB want to have one single thread pool across like all the modules which link against TBBs. That's why it's like advertised to be a dynamic library. And by the way, it's available on Conda. Moreover, it's available on like many channels right now. So Conda Forge has TBB as well. And we actually talked about the Python model for TBB. So it leverages the TBB library itself to like expose this composability to Python world. Am I answering the question?
There's a Python wheel for TBB? Yes.
Yes, by the way, there is a wheel already, yeah.
Okay.
So it's available, become available recently, yep.
And is there any documentation related to how other C extensions can use that wheel?
So that's an interesting question, pretty much related to what David was talking about. So right now, the Python side of like TBB, so the part which is represented in Python, it is pretty much like this command line, and it's up to like you guys if you have some requests for us, like what kind of API you actually want. So it's not about like TBB brings like the new parallel programming paradigm to Python. It actually just solves this composability problem here, specifically. Thus, the Python model for TBB just has this command line interface. Yeah, that's pretty much how it.
Hi, on your last slide, when you were saying, well, if just, sort of putting comments or decorating a loop to make it parallel, and saying, well, isn't that just going to look like OpenMP? I think OpenMP is awesome, but I have a hard time imagining how an elegant clone or counterpart of that in Python, because of how complex Python is as a language. Have there been any successful, or what attempts have there been at sort of an OpenMP-like way to achieve parallelism in Python?
I don't think we've seen a successful case. I think that's why I've posed the question. I think with the comment was there mostly just to kind of state this is an idea. I've seen it done in other languages. Obviously, they've done it in C. It's just we can play with it. I've yet to see anybody else in the community think that it's a good idea, but if if you think it's a good idea, it may be worth a shot. And if you come up with some use cases, maybe we can talk afterwards of like what your thoughts are on it.
Sure. I mean, it's just been my experience with like numerical astrophysics type applications that, OpenMP is just like, it's just a great way to take, a code and instantly, it's just so easy to use.
Okay. Well, yeah, let's talk.
Yeah.
Thanks.
Thank you.